The surprising truth about photonic computing is that the first big win is not computing. It is moving data. Most near-term value comes from replacing hot, resistive electrical plumbing with light. As of 2026, optical communication is already the strongest practical deployment. Fiber links, data center transceivers, and wavelength division multiplexing are mature workhorses.
Optical switching is still largely in research, and general-purpose optical logic remains commercially immature. That split matters, because it tells you where reality is and where hype still lives. If you care about AI infrastructure, start with a simple observation. Modern systems increasingly burn energy and time just shuffling bits around, chip to chip, across a package, between racks, into memory, and back again. Arithmetic is no longer the only cost center, and in many workloads, it is not the dominant one. Photonics targets that imbalance directly by shifting selected data paths into the optical domain. When people say optical compute, they often picture an all-optical CPU. That is not the practical story. The practical story is hybridization. Light does what it is naturally good at: fast propagation, interference, modulation, and wavelength multiplexing. Electronics keep doing what they are good at: control, memory, nonlinearity, error correction, scheduling, and digital precision. Think of optics as a high-bandwidth data plane, with electronics as the control plane. One reason optics stays compelling is parallelism that feels almost unfair. With wavelength multiplexing, you can send multiple channels through the same physical waveguide. With interference and phase shifting, you can implement linear operations at high throughput. Diffraction and carefully designed structures can perform transforms that look like math, but happen as physics. That is why so many optical accelerator concepts focus on linear algebra, the same class of operations that dominate neural networks. Neural workloads did not become central by accident. Back in 1998, gradient-based learning for document recognition helped cement a durable template: convolution-like operations, matrix math, and differentiable optimization. Today, that template shows up everywhere from vision to language models. So optical approaches keep circling the same target: fast, dense linear transforms, especially for inference, where approximate results can be acceptable. But there is a trap here, and it is the trap that separates lab demos from production systems. A device can look stunning in isolation and still lose at the rack. The true question is end-to-end energy accounting. Once you include laser power, modulation, photodetection, electrical to optical conversion, thermal control, calibration, and digital correction, a system that wins at the photonic core can easily lose after you pay the full operational bill. Precision is the next hard constraint. Optical systems tend to drift. They face shot noise, thermal variation, and fabrication variability. Detectors are not perfectly linear. Materials absorb light. Couplers lose power. So the practical question becomes, how many effective bits of precision do you get, continuously, under real conditions? Analog optical linear algebra may be fine for some inference, signal processing, search, correlation, or optimization. It may be unacceptable for workloads that demand tight numerical accuracy or stable reproducibility over long runs. That leads to the most underappreciated metric in photonic compute: calibration burden. How often do you need to recalibrate? How long does it take? Can it be automated? Can it be done quickly and infrequently enough that an operations team can live with it? If calibration requires constant attention, you do not have an accelerator. You have a science project with a service contract. For strategy leaders, calibration and serviceability should be treated as first-order performance metrics, not a footnote, not a vendor detail. A procurement team should ask about drift, accuracy loss over time, thermal sensitivity, and module replacement time, with the same seriousness as throughput and latency. Packaging is where many real-world outcomes will be decided. It is not enough to have a good modulator, or a good detector, or a good waveguide. You have to package photonic devices, lasers, thermal control, and electronic chiplets at scale. You need yield, you need test, you need repair pathways, you need acceptable cost. Over time, packaging may dominate strategic advantage more than any single optical component. It also creates a coordination problem. Even if the physics works and the engineering works, modular infrastructure needs standards, interoperability regimes, telemetry norms, failure reporting, calibration metadata, benchmark disclosure. Without these, optical I/O risks becoming a set of vendor-specific silos, hard to mix, hard to audit, and hard to maintain. That slows down inference factories and high-bandwidth scientific computing, even when the parts are available. Benchmarks are the battlefield where these arguments get decided, and also where they get manipulated. The central question is benchmark integrity. What protocol prevents optical TOPS claims from ignoring conversion losses, calibration time, accuracy drift, cooling overhead, and data movement? Procurement-grade benchmarks must measure useful workload output, not isolated optical operations performed under favorable boundaries. This is where software infrastructure quietly becomes strategic. Reproducible analysis environments like NumPy for arrays, R for statistics, and ImageJ for measurement workflows are part of the operational substrate. They are how teams compare experiments, validate claims, and detect drift. They also make results portable across labs and vendors. Without shared tools and shared methods, you get beautiful graphs that cannot be reproduced, and purchasing decisions you cannot defend. The talent implication is direct. Photonics cannot sit in a corner as a novelty team. Effective adoption links 4 disciplines: integrated photonics, advanced packaging, computer architecture, and numerical benchmarking. And that group must stay connected to networking and data center operations, because most value is system level, not component level. Zooming out, the maturity timeline is easier to read if you stay grounded. From 2026 to 2050, the likely scaling path is optical I/O, co-packaged optics, photonic interconnect, and specialized accelerators where system-level energy and latency gains survive conversion overhead. From 2050 to 2100, hybrid optical-electronic fabrics could become normal in AI and HPC if calibration, packaging, thermal control, and interoperability mature. Beyond that, deeper futures remain contingent, not on imagination, but on maintainability, manufacturing continuity, and whether analog precision can be made operationally routine. It helps to remember that nanophotonics is not speculative in the basic sense. In 1998, extraordinary optical transmission through sub-wavelength Hole arrays demonstrated strong, non-intuitive throughput in engineered nanostructures. That result helped establish a foundation for dense optical structures and engineered light-matter interaction. So the device physics is real. The question is integration, control, and economics at scale. If you are allocating capital today, the disciplined posture is not to bet on wholesale replacement of CMOS CPUs or GPUs. The disciplined posture is to fund what can be benchmarked and purchased as infrastructure. Optical interconnect evaluation, co-packaged optics testbeds, packaging capability, metrology, calibration automation, standards participation. Those are the investments that let you say yes later with confidence, instead of saying yes early on faith. A simple internal diagnostic can clarify your next move. Which workloads are limited mainly by data movement, not arithmetic? What measured energy and latency gain would justify optical I/O procurement this year? And who in your organization owns photonic readiness, networking, accelerator architecture, packaging, or operations? The enduring takeaway is this: photonic computing will matter first where electrons are failing, in the cost of moving information, not the act of thinking itself.